You ever wonder how a single massive server can run hundreds of different websites for hundreds of different customers, all at the same time, without them ever bumping into each other? Well, the magic behind all this is called virtualization. It's this collection of brilliant technologies that lets one computer act like it's many. Today, we're going to unpack the two heavy hitters in this world, virtual machines and containers. All right, let's get into it.
So here's the fundamental puzzle they were all trying to solve. You've got one physical machine, right? But you need to run multiple apps, or maybe even entire operating systems on that single machine. And the trick is, you have to keep them totally separate. They need to be isolated, they need to be secure, and each one needs to be convinced it has the entire machine all to itself. This is the big question that led us to both VMs and containers.
The first major answer to that question was the virtual machine, or what we all just call a VM. And this was a total game changer. It allowed us to take one super powerful server and just carve it up into a bunch of smaller, totally independent digital computers. And to really get how that works, we got to talk about the special software that pulls all the strings.
That software is called a hypervisor. You can think of it as a strict but fair manager for the computer's actual hardware. It sits right in between the physical machine and all the virtual ones, and its job is to take all the requests for CPU time, memory, and storage, and then carefully hand out the real resources among all the guest machines that are running. Now, you should know that not all hypervisors are created equal. They basically come in two main flavors. First, you have Type 1 hypervisors. These run directly on the server's hardware. We call this bare metal. These are the performance champions, the stuff you find in massive data centers, like VMware's vSphere or Proxmox. Then you have Type 2. These run just like any other app on your computer. If you've ever used something like VirtualBox or VMware Fusion, to run Windows on a Mac, yep, you've used a Type 2 hypervisor.
So, what is this VM the hypervisor is creating? Well, it's an entire computer, but one that's built from software instead of silicon. Each VM gets its own virtual hardware and, this is the critical part, it runs its own complete copy of an operating system. It is totally unaware of any other VMs on the same machine. This amazing isolation is the exact technology behind what's called a virtual private server, or VPS. When you rent a VPS, you're literally just renting one of these software-based computers.
And when you look at this stack, you can really see the cost of that perfect isolation. Look at all these layers. For every single application you want to run, you have an entire guest operating system with its own kernel, its own files, all of it, taking up space and memory. Now this is powerful, for sure, but man is it heavy. And for years, developers kept wondering, isn't there a lighter way to do this? And that question, well, it leads us right to the next evolution in this story, containers. They took that core idea of virtualization, isolated environments on one machine, and just completely reimagined it for speed and efficiency. So the game-changing difference is right there in the definition. A container doesn't need its own whole guest operating system. Instead, it just shares the kernel of the host operating system. It doesn't pretend to be hardware. It just puts up some walls to create a small, isolated space for a single app to run. And that one difference, it changes everything.
This is honestly the best analogy for it. If VMs are like separate houses, each with its own foundation and plumbing and electrical system, then containers are like apartments. They all live in the same big building, and they share that core infrastructure, the operating system kernel. But they each have their own private space and their own locked doors. This is done with some really clever Linux kernel features like namespaces, which give each container its own view of the system, and cgroups, which act like a utility meter, limiting how much CPU and memory each apartment is allowed to use.
And you can really see the difference when you put the two stacks side by side. Look at the VM on the left. See that thick guest OS layer? Now look at the container stack on the right. It is so much leaner. The container engine, something like Docker, it talks directly to the host OS. By just shedding the weight of an entire extra operating system for every single app, you gain a ridiculous amount of efficiency. Just how much efficiency are we talking about? Well, while a new VM might chew up hundreds, maybe even thousands of megabytes of disk space for its OS, a brand new container can take up as little as 12 kilobytes. No, that is not a typo. It's that small because it's not a full OS copy. It's just a tiny bit of metadata that points to files that are already shared. It's incredible.
This all sounds amazing, right? But it brings up the million-dollar question. What's the actual performance difference? Does all this abstraction and isolation slow things down? Let's see what the research actually says.
So you'd probably assume that the closer you are to the actual hardware, the faster you'll be. But check this out. It's not quite that simple. This chart shows a database benchmark. That blue bar on the left, that's the raw physical hardware, or bare metal. Now notice the container, the orange bar? It actually finished the job in less time. How on earth is that possible? Well, it turns out that these virtualization layers can introduce their own clever optimizations, like really advanced caching. This table breaks it down across a bunch of tests, where 100% is the speed of the bare metal hardware. And I mean, look at storage performance or VMs, up to 197%, or network for containers at 112%. In some very specific cases, virtualization can actually be faster than the real thing. It's wild. Okay, so those are specific cases, but for most of what you'll be doing, here's the general rule of thumb to remember. The performance overhead is incredibly small. For containers, you're usually looking at less than a 5% hit, and for modern VMs, it's typically around 10%. Honestly, for the massive flexibility you gain, that's a trade-off pretty much everyone is willing to make.
So with such small performance differences, how do developers actually choose which tool to use in the real world? Well, it really all comes down to the specific job you're trying to do.
For creating consistent development environments, for instance, a lot of people turn to tools that manage the VMs for them. Vagrant is a perfect example. It's a tool that basically automates hypervisors like VirtualBox or VMware. A developer can just write a simple text file defining what the computer should look like, type one command, Vagrant up, and boom, Vagrant automatically builds and configures a complete virtual machine for them, exactly identical to the one every other developer on the team is using.
So when you strip it all the way, it really boils down to this. You choose a virtual machine when you need maximum hardcore isolation. Maybe you need to run a totally different operating system like Windows on Linux server, or you have extreme security requirements that demand true hardware-level separation. You choose a container when your main goal is to package up a single application and all its little dependencies, making sure it runs the exact same way on your laptop as it does in production. It's all about speed and portability.
And that brings us to our final thought. What's really fascinating is that the line between these two worlds is starting to get blurry. There are new projects like Kata containers that are now running containers inside incredibly lightweight, stripped-down virtual machines. The goal is to give you the best of both worlds, the strong, hardware-enforced security of a VM, but with the speed and the portability of a container. It leaves us with a pretty interesting question to think about. Is the future of computing a clever mix of both?